Let's get started here. I'm sorry about that. It's sitting on my windowsill. It's a little spiral notebook. Thanks. I left my notes on my desk. Okay, guys. Nice to see you again. Let's think here in terms of announcements and so on. Next week, your reading assignment is due, what, Tuesday? I guess Tuesday, right? Because this every other week is a nano quiz, and every other week is reading assignment. How many of you guys have identified a paper you're going to read? How many of us have opened the reading assignment? How many of us are going to consider opening the reading assignment? Okay, there we go. Weirdly, that still doesn't cover most of this, like a large fraction of this room. Yeah, so the reading assignment really is just, this is a graduate course. You guys should be engaged in this area as a research discipline. So it's just a chance to read a paper you're interested in and write like a paragraph. It's really not a big deal. As part of that, if you guys are looking for suggestions in a particular discipline, you're more than welcome to contact me or Sebastian or anybody in our group, and we can try to suggest some. Reality is that many of you come from research areas that we don't know all that well, but we're happy to dig around a little bit. If nothing else, we've developed a bit of a sniff test and can tell you if something looks crackpot or not. And of course, as we know, there's like this kind of long tail in academia of kind of low quality research papers, and this discipline is no different. Yeah. So if you're not used to kind of picking out papers and figuring out which ones are good, which ones are bad, all that good stuff, just let us know, and we'll help you out. Other than that, when is your homework due? Is that next week or the week after? The week after next. Okay, great. Yeah, there were some people in my office hour yesterday, but only like 2 or 3. It was very lonely. So there's that. Cool. Any organizational questions about A3? It's a pretty straightforward class. Okay, great. All right, so we're going to pick up where we left off, which is finally doing geometry for once. And that's hopefully where we'll stay for the rest of the semester. So if you recall our story so far, we're talking about smooth curves. We decided smooth curves are not functions, right? They're sets of points sitting in Rn. Typically R2 or R3 is what we'll draw here, but the case doesn't really get any more complicated in higher dimension. Yep, and it's one-dimensional in the sense that if I grab any point on a curve and I draw a little neighborhood around it, then I can come up with a function which is 1D and maps into it, right? That was our basic condition, yep? And one of the big philosophical points that we really hammered home last time, I hope, is that doing geometry on curves is not the same as doing calculus on functions of one variable, yeah? In particular, there are many different functions that all trace out the same geometric object. And one of the really boring, tedious things you have to do in the theory of differential geometry is every time you propose some measurement and you write it in terms of derivatives and so on, you have to go back and double check that if I had a different function that traced out the same curve, I would get the same measurement. Yeah? And so the example that we covered last time was arc length, which, if you recall, conveniently is on the screen here. This thing a priori could be dependent on your parametrization, right? I wrote it in terms of the derivative of gamma, and as we know, velocity depends on how fast you drive along the curve. But then we went back and we double checked that indeed, if we took another curve that traced out the same thing, or another function that traced out the same curve rather, you get the same value, which is what we needed. Okay, so everybody with us so far? Fabulous. And then the very last thing we did at the end of the class, which probably got rushed because I got all excited and wanted to finish off a little bit more than we got to, was this idea of parametrization by arc length. The idea being that if essentially I want to write measurements in terms of what, like I think of gamma of t as sort of the position of a car as a function of time driving along the curve, right? Then the fact that the car is speeding up and slowing down as it drives along the curve is relevant. Right? And so one way to kill that is to just think about a car that drives at 1 mile per hour or whatever, right? Just with constant speed. And then anything that car measures has to do with the geometry of the curve, right? Because it's not accelerating. And so this is one kind of hack to get around having to check every single calculation you do being invariant to parametrization, is to just kind of choose a canonical one geometrically rather than assuming you're given a function gamma. Yeah? Of course, arc length as a measurement on a curve parameterized by arc length is kind of a weird thing to talk about, right? Instead, we'll talk about other measurements you can do once you kind of have arc length, and now you want to do something more interesting. Okay? Incidentally, one thing that we didn't check in class was that arc length has anything to do with length. Right? In particular, that this formula has anything to do with the length of a curve. That's something you guys should check at home if you haven't seen that before. Yeah? Or you can just Google it. There's plenty of like kind of calculus style motivations of that. Okay. So today, we're going to talk about something which will essentially motivate the first third of our course, which is curvature, right? Because essentially, when you talk about local geometry, it's all about bendiness and how to measure that, right? And we all have a lot of intuition about what curvature means to you, I hope. But oftentimes when we talk about it in a calculus sense, again, we end up confusing a little bit, what's a function and what's the actual geometry sitting underneath it. Right? So I think the typical intuition you hear in calculus class is that curvature and second derivatives have something to do with one another, right? When your second derivative is high, something's kind of bendy. And that's essentially the notion that we're going to try and formalize today. Okay? Right. So let's do that. So far, we're given a curve, and our curve for now is going to be just in the plane, and we're going to think about what it means for a plane curve to have curvature, then we're going to lift into 3D, and then briefly mention what happens in n dimensions, because I'm desperate for somebody to come up with a cool application for it, although I've yet to, in the many times I've taught stuff like this, I've yet to find somebody that has. But you guys could be the ones. Okay, so let's say that I have a curve in the plane, right? That's a 2. And in addition, my curve is PBAL. You guys remember what that stands for? Parametrized by arc length. Yeah. There are a few textbooks that actually use this acronym quite a bit. Okay, so typically the way that the differential geometry people will remind you of that is they'll use the letter S. So we'll say that gamma of S is gamma parametrized by arc length, and S, I guess, is the AL part of PBAL, yeah? Okay, so first of all, one thing that we proved at the very end of class last time, let's define a vector T of S to be gamma prime of S, in other words, the first derivative. And if you recall, what do we learn about gamma prime when it's parametrized by arc length? What's the norm of this thing? 1, yeah? Okay, so in other words, by the way, when I use this triple equals sign here, this is sort of like saying for all S, this thing is identically equal to 1, right? It's like one extra line to really drive home the fact that these things are equal. Yeah, like not just for a single S, but for like some range. Yeah, this is where like math notation starts to get a little expressive rather than precise. Yeah, okay, for all S. So we can start to think a little bit about it. And so remember that T is like the velocity of my really boring car that's driving at constant speed. Yep. And the question that I posed to you guys last time, but we didn't really formalize in a careful way, is can that car feel acceleration? And the answer is absolutely yes, right? In particular, here's my car, and it's driving along the board, and it's twisting around all kinds of crazy loop-to-loop ways. It's doing Tokyo drift kind of thing here. Yeah. Then what happens to my car as it drives? Well, even if I drive with constant speed, thanks. Now I can stop stalling. The car itself actually feels some acceleration, right? The passengers feel acceleration simply because the car is driving along this loop-to-loop. Yeah. And that acceleration is a function of the geometry of the curve, not my bad driving. Does that make sense? That's what we're trying to parcel out. Okay. So how do I sense that? Well, T is the first derivative of a curve, PBAL. Yeah? So what do you think I'm going to do for acceleration of the car? Yeah, differentiate it again. Okay, so in particular, I'm going to define a very particular object, which I'm going to call kappa of S n of S, which is going to be gamma double prime of S. Or the more typical thing to write is T prime of S. Hopefully you guys agree that these are equal to one another. Yeah. And now the question is, well, why are there two things here? Yeah. And essentially what's going on is that I'm going to think of n as a unit vector and kappa as its norm. Okay. which is always an okay thing to do. Okay, so let's fill in our picture a little bit more, specifically in the two-dimensional case, because there's a lot of nice things we can do in 2D that don't lift a higher dimension. For fun, I'm going to see how far I can get without my notes before this becomes a hot mess. Okay. So here's our curve. Let me draw it in a convenient fashion. And in particular, okay, here's a point. Here's gamma of s. And here is t of s, right? So my car is driving this way this time. And since I'm specifically on the plane, one thing that I can do is stick a little clock face right on the blackboard here. And in particular, I suppose my clock face is going to be, by convention, rotated 90 degrees from a normal clock. I can measure this angle here. Right? So this is just the angle of t of s as my car drives around. Yeah? So like when my car is pointing north or up, then theta maybe is 90 degrees. Yeah? Okay. By the way, if I rotate my whole curve, notice that the theta function will change too. Yeah? So this isn't like a particularly useful measure of geometry. Okay? Right. So I can think of theta s kind of like I'm holding a compass as I drive the car and it's telling me what direction I drive. Then one thing I can do is I can say, okay, well, I can write an expression for t of s in terms of theta. This is where I'm specifically taking advantage of the fact that I'm doing two-dimensional math. Yeah? In particular, I can write the following. Right? And hopefully we can all agree that this is one way to get t from theta. Right? Okay, so if I want to talk about curvature, what do you think I'm going to do? Well, I'm going to differentiate this thing. Yep. So if I differentiate it in s, what do I get? Well, okay, by the chain rule, let's see if I can manage to get this right. I get minus theta prime of s times sine theta of s. And similarly here, I get theta prime. Have I managed to go 5 minutes without a sign mistake? Yeah, so we're doing better than last time. Okay, right. So in particular, I can pull out this factor of theta prime. And what I'm left with is a unit vector, right? There's a sine and a cosine here. So what is this guy's name? This is kappa of s, yeah? This is curvature. Okay, I can write curvature of s times, this is sine, minus sine comma cosine. Notice that t was cosine comma sine. Right? So one thing I can do is that, right? This is just taken by taking this vector and multiplying it by this very specific matrix. Yeah? Anybody know what this matrix does? Yeah, it's just rotation by 90 degrees. Counterclockwise or clockwise? Any guesses? I'm going to be honest, I can never remember, so I'll let you figure it out at home. Okay, so this object is n of s. And for one thing, this fills in a little bit of intuition that you guys probably had just by virtue of my calling it n, which is that it's normal to the curve, right? Normal means perpendicular. And of course, what did I do to get this vector? I took the tangent vector and I rotated it 90 degrees. Yeah? So what's going on in this picture? Well, now I have this other vector n of s. It's orthogonal. And then the magnitude of t prime is a scaled, is the curvature here. Okay? Everybody with me so far? Fabulous. So this actually, from my perspective, is really the right way to think about curvature of a curve, right? Is that the curvature is nothing more than this theta prime. But you think about it, what is theta prime? So if I'm a driver and I'm driving along this curve, theta prime is just the direction of my steering wheel, right? If my steering wheel is straight, then what I'm saying is don't turn the car at all, right? Just don't change the bearing of the car. And as I turn my steering wheel more and more, well, that thing is affecting the curvature of the curve, so it all kind of fits together. There's nothing too exciting here. Okay, and that's exactly the picture that we get for what we'll call the moving frame in 2 dimensions. And notice that as long as my curve is not a straight line, these two vectors t and n, well, I guess even if my curve is a straight line, these two vectors form a basis for R2. This is a weird basis, right? It's kind of the basis from the perspective of the driver as he's driving along the curve. Yeah. So in physics, I think you call this what, non-inertial or some damn thing. I don't know, I'm not a physicist. Okay, so that's our curvature picture so far. But notice that I kind of cheated, right? Like I set out this whole philosophy that in geometry we shouldn't be using coordinates, and then the very first thing I did was write down coordinates here. For one thing, it's pretty clear that like this curve, like if I took my curve and I just rigidly rotated it, curvature kind of wouldn't change for the curve, right? Because it's theta prime. But really somehow there's like a little bit of a philosophical point, which is that differential geometry shouldn't be, well, it should be coordinate invariant. It shouldn't be coordinate dependent, yeah? And then somehow referring to x and y components is a bit of a hack, right? Because x and y are sitting underneath my curve. They don't have anything to do with the curve itself. It's a total boring philosophical point. So here's my question. How would I describe my curve without referring to coordinates? How would I describe its geometry? It's kind of a weird circular question, right? The only thing I have is the plane that the curve is sitting on. Yeah? Norms? A norm of what exactly? Well, the norm of the unit vector is 1. Yeah, you're absolutely right. So the curvature is basically the only object that we have anything that seems to tell us something about geometry. Yeah, and the question you could ask is that enough? Does that tell me everything I need to know about the curve? Any of us vote yes? Any of us vote no? Any of us just like can't even right now? Yeah. Okay, so, so somewhere between 1 and 3 wins today. No, so the basic trick in differential geometry is if the only coordinate frame you have access to is the tangent and normal, right? We got those from parameterizing the curve by arc length, so those are fair game. Well, then if I want to describe the geometry of the curve, all I can do locally is describe it in the frame that I just wrote down. It's turtles all the way down. Yeah? And in particular, I can do a really bizarre thing, which is, okay, so notice that we just derived the first relationship here, right? That du over ds of t is kappa n, kind of by definition. One additional claim is that if I differentiate the unit normal, I get back minus kappa times t. Let's double check that real quick. Every time. I hate these things. Had a meeting with Sebastian this morning where the same thing happened with a cup of coffee, and it wasn't great. Okay, so remember, what is n? Well, in some sense, so if we call that matrix J, right, this thing here, then n is equal to J times T. Yeah, it's a good acronym. So if I differentiate in arc length, what do I get? Well, maybe I'll write dn ds equal to J is just a constant here, right? So it's J times dt ds. Yeah. What's dt ds? Well, that's kappa times the normal. So that's minus J kappa times J times the normal vector. Right? So if rotating the tangent vector one time by 90 degrees got the normal, rotating by the same 90-degree angle again gets me what? Minus the normal, right? Or minus the tangent, rather. Right? So this is minus kappa t, and that completes this set of relationships, right? So in other words, what does this tell us? This tells us that I can keep differentiating my curve as many times as I want by arc length, and I'm just going to keep flipping back and forth between normal and tangent direction. So there's like kind of no more information hiding there. And that makes sense because the plane is flat. There's only 2 dimensions to be had. Okay, and so great. So this is kind of this funny scenario where actually what we've done is we've used coordinates that we grabbed from the curve to describe the shape of the curve itself. This makes a lot of sense, right? Because essentially all it's saying is that locally to describe geometry of an object, all I have at my disposal is how fast I turn the steering wheel as I drive this over this object in the plane. Is that going to be true in 3D? No, right? Because I can turn the steering wheel or I can like jump, yeah? And we haven't figured out how to leave the blackboard yet. Okay, there are like so many, like millions of different ways to describe what curvature means to you. Another very popular one in the classical differential geometry world is this one, where if you take 1 over curvature, this is the radius of the circle which touches the curve with the most if you do the Taylor series, this is the most contact you can have between a circle and a generic curve like that. Right? So this is called the radius of curvature, and that'll come back when we talk about fundamental forms. Okay, and it's a nice picture. This is it's called the osculating circle. Does anybody know what that means? It's Valentine's Day. Huh? Yeah, they're kissing. I think that's nice. Okay, right. So we just derived a measurement that we can get from a curve, right? We can go from, and essentially what we showed is that because we got it from parametrization by arc length, this function kappa is really a function of where you are on the curve. It's not a function of the function gamma. Hopefully this distinction, like I can stop being pedantic about it soon. Yeah. There's an inverse question which is kind of interesting, which is, let's say that I give you kappa of S. Is that enough to get the curve? What was that? Boundary condition. You're absolutely right. If I take the curve and I rotate it 10 feet to the right, then kappa doesn't change. So let's say that I give you the curve and I give you its position at s equals 0 and its tangent at s equals 0. I see nodding, and you're absolutely right. In fact, this is the fundamental theorem of the local theory of plane curves, which is actually, I think, longer than the statement of the theorem itself, which is that up to rigid motion, this function kappa of S is unique for a given curve. In other words, if two curves have the same function kappa, they actually are the same piece of geometry, at least after you kind of rotate them to a line. Yeah? And in fact, we can prove that. It's a pretty straightforward thing to prove, and it's more or less just taking the steps we did here and flipping them backward. You guys see that? So if I have kappa of S, right? I'm going to sketch this out in like 3 symbols or less because we're a little behind in our class here. If I have the function kappa of S, well, remember that that's theta prime of S. Yeah? So if I integrate this thing, then in effect what I have is theta of S up to a constant, right? So I know the tangent as a function of arc length. Cool. Okay, so if that's true, then I have the unit tangent up to rotation, right? Just by taking cosine and sine of this thing. Yeah? And remember that this thing is gamma prime. So if I integrate one more time, then what I get back is gamma up to a constant shift and rotation. Yeah? So that's the sketch of the proof there. If you want to see the full proof, it's in the course notes, and it's really like not much more than like 1 or 2 words per arrow here. Yeah? Yeah, I think it's a cute theorem because essentially the statement's shorter than the name. Okay, right, and there's so many different pictures that you can draw when you talk about things like curvature. And another nice one that's going to come up. Many of the things that we're drawing here are largely so that when we do surfaces, you'll see that it's like the 2D analog. Another picture is this thing called the Gauss map. Gauss is a big name. He's going to show up a lot in the coming weeks. So the idea of the Gauss map is it's the map from points on the curve to points on the unit circle, which are the tangent vectors to the curve. So sometimes it's like gamma prime, but ignoring that function gamma and going directly from points on curve to points on circle, right? That's the sort of geometric object. And yet another kind of picture you can draw is that, when you measure curvature, you're kind of measuring how fast that clock is rotating about its center. And that's sort of the idea behind this proof here. So you're just undoing that. Yeah? Okay, great. So, right. Oh yeah, and that object's called the Gauss map. There's one more thing we should mention before moving on. Let's say that I have a smooth curve. Erase that because it's not saying anything anyway. Let's say the gamma is smooth. So in particular, it has a well-defined tangent, and that like gamma of 0 equals gamma of, I don't know, some other point S. Yeah? So geometrically, what is this? What are these symbols telling me? This is telling me I drew a curve, whatever it is, and eventually it met back up on itself. Yeah? Okay. And in fact, maybe we'll say that this is true for S plus like that. So essentially it's a periodic function. So it really just keeps going around and loops around this thing. Okay? Then what can I say about the integral from 0 to S of kappa of S bar d. So remember that kappa is theta prime. Yeah? So this is theta of s minus theta of 0. Yeah? But remember that these two thetas describe the same tangent vector. Yeah? So what do I know about this number? What was that? 0? Not quite. Also could be 2 pi. In this case, it's 2 pi. What if I have a loop like that? Yeah. So what I know is that this thing is equal to 2 pi times k. This is a k and not a kappa, in case you were wondering. Unfortunately, we're stuck with this. It's what all the textbooks use too. In particular, k is an integer. Yeah? This just falls from trigonometry argument, right? That's all you needed here. Notice this is like slightly amazing, right? What is this telling me about my curve? I have this real valued function kappa that I got by, measuring little changes in my steering wheel when I drove over the curve. And when I integrated this thing over time, I got an integer. Yeah? What is that integer, by the way? Like intuitively, does anybody want to share an explanation? Like what is this thing telling me? Magnus, what's it telling me? Yeah, it indicates how many times the car looped around itself, around its path. Yeah. So this thing has a name. Typically, we divide it by 2 pi so that you actually get an integer. And this thing is called the winding number of my curve. And there's like kind of a topological theorem that, if you state it this way, sounds kind of scary, but now that we've seen the proof, really isn't. Which is that if I smoothly deform my curve, W of gamma isn't affected. Right? Because again, this is just the number of loops. Yeah, that's the picture behind the scenes. But really, all it's saying is that, like, well, the t's meet up, right? If I take the integrand and so if I smoothly deform the curve, then in particular, this function k of s smoothly changes as I deform the curve. Yeah, and okay, well, W is the integral of a function that's smoothly changing in time. It's also an integer. What's the only function that is smooth in time and also an integer? Constant, yeah? So in other words, if I smoothly deform my curve, the winding number doesn't change. And that makes a lot of sense. This is a topological fact. Essentially what it's saying, okay, can I homotopy this curve and make it into a single loop? Like if this is a piece of string, can I deform it into a single loop? Absolutely, right? I could just pull it tight, yeah? But what has to happen at some point when I do that? Can I do it and keep it as a smooth curve the entire time? No. Because if I did, this thing would break. Yeah? So anyway, it's kind of an interesting little topological fact. If I take a curve and I try to untwist it, then necessarily at some point in time, if that curve had a winding number that wasn't 1, then when I untwist it to something that does have winding number 1, at some point in time, there's a kink that got formed. Yeah? So it's an interesting little, like, fun topological fact. Okay? Everybody with me so far? Cool. All right, so the last thing we're going to do in the smooth case before we go to discrete curves is the 3D version of this story. And it's quite similar. So this object is called the Frenet frame. By the way, the 2D one is sometimes called the Frenet frame. I think this is the more famous version. So the idea here, let's go to the other board. Okay, and now I'm going to use my notes because this is the kind of thing that I could get wrong. Let's prove a very small, boring, uninteresting lemma. Cool? So this happens to be my favorite lemma from all of math. If you took my undergraduate class, you also have seen this. Let's say that I have a vector v of t. It doesn't have to have anything to do with arc length. And in addition, I know that the norm of v of t equals 1 for all time, right? This is a triple equal sign again. Yeah? Then what I want to know is the relationship between v and its first derivative. In fact, let's just do this calculation real quick. So for convenience, let's square the norm. Yeah. So what do we get? We get that 1 is equal to the inner product. Actually, in this class, let's do v of t dot product with v of t for all t. Yeah. And if we differentiate both sides in time, what's the derivative of 1 with respect to t? 0. You guys are getting the hang of this. What's the derivative of the right-hand side? Well, just by the product rule, right? This is 2 v of t dot product with v prime of t. You guys see that? Okay, geometrically, what is this theorem telling me? It's telling me if I have a unit vector as a function of time, and I take its derivative, then the derivative has to be orthogonal to the unit vector, right? So in other words, if v is changing like that, then v prime looks like that. Cool, kind of slick. Okay, so why does that matter? So similarly, let's do one additional equally exciting lemma. Let's say that v of t dot product with w of t equals 0. So now I have two orthogonal vectors that are sliding around, right? And now let's differentiate this thing. So what do I get? Well, I get 0 is equal to v prime. I'm going to drop the t's because I'm lazy. Plus v dot w prime. Yep. Or in other words, v prime dot w is equal to minus v dot w prime. So what is this saying? This is saying the component of v prime in the w direction is minus the component of w prime in the v direction. This is a nice symmetry here. Okay? So these are the little relationships we're going to use to derive Frenet frame in 3D. Okay. So here's the basic trick when we do 3D frame. So now I have a curve of S which goes into R3, and again he's P, B, A, L, our favorite acronym here. Okay? Now by the first lemma, right? So first of all, let's define T is equal to gamma prime, right? That's still the unit tangent, just like before. Notice by the first lemma, what did we just show? We showed that if I take t and I differentiate it in time, it's some vector that's orthogonal to t. Right? That's what the first property shows. Okay? So let's define t prime. Now we're going to just define it to be kappa n, where kappa is greater or equal to 0. Right? So we're going to assume, by the way, that all of the derivatives of gamma are non-zero, just for simplicity here. Right? And the way that I do that is I say, well, I take t prime, it might not have unit length, so I put its length here, and what I'm left with is a unit vector. Cool? Cool. Okay. So here's the thing. In 2D picture, we're done, right? We now have two vectors. We're in R2. Life is good. In the 3D picture, we're not, right? We need a third vector. What do you think? How are we going to get it? Yeah. You know, if you have two orthogonal vectors and you want a third one, there's a good hack to get it, right? Just take the cross product. So let's do that. Let's define B to be the cross product of T cross N. And this is where I'm going to rely on my notes so that I don't make a sign mistake. Okay? Anybody know what B is called? The binormal. Yes, thank you. All the insightful people that looked at the screen there. And why is that? Well, it is normal to the curve and to the normal. So it's the binormal. Okay. So, everybody with me so far? So, what do you think we're going to do? Well, again, remember, like the basic hack in the differential geometry of curves is to keep writing everything in terms of itself, right? So we figured out that if we took t prime, we could write it as kappa times n, where kappa is curvature. So what should be the next thing that we do? Well, one thing we could do is take n prime and see what happens. Yeah? Okay, so let's do that real quick. So, right. So here's our normal vector. How do I want to do this? Yeah, okay, great. Right, so first of all, n prime. What do we know about this guy? So remember that n is a unit vector. Yeah, there we go. Getting the figure. I never ask you guys hard questions. Okay, right. So if I want to, right, I can expand n in a basis. Right? And I can just throw out one of those three terms parallel to the normal, just for laziness sake. Yeah? So what am I going to do? Well, I'm going to say that that's n prime dot product with the tangent times the tangent plus n prime dot product with the binormal times the binormal. Right? All I've done is expand in a basis here. Does that make sense? This is just a hack. Okay. Now what do you think I'm going to do? Well, right. So let's take a look at the second lemma that we showed. We showed that if two vectors are always orthogonal, and I take the dot product between one of the derivatives and the other guy, then I can swap those two as long as I change sign. Yeah? Okay, so n and t are orthogonal, right? So I can just pop this guy onto the other one, and that's perfectly fine as long as I change the sign. Yeah? So in other words, this thing is equal to minus t prime dot n times t. What is this thing? This scalar? It's the component of t prime in the n direction, but t prime is kappa times n. Yeah? So this is just curvature. Sneaky, huh? Okay. Plus some other thing. Times b. Okay, so apparently we need two numbers. We found one, so what are we going to do with the other guy? Well, we're just going to give him a name. We'll call this thing torsion, which is a tau. Okay? Cool? Cool. So going back to our Fermat frame equations, notice we verified the first guy kind of by definition, and the second guy half by definition and half by, you know, a little sneaky trick, and the other half by definition. Yeah? And of course, the only third thing that we have to do to complete our nice trick here is differentiate the binormal and show that we get this third relationship here. So let's do that real quick. I love these calculations because they're really easy. Okay. So by applying the same logic that we had before, we know that the binormal b prime, well, we know that it's orthogonal to b, right? So we can go ahead and throw that piece away. So this thing is really equal to b dot the tangent times the tangent plus b dot the normal times, b prime times the normal. Right? This is the same trick we applied over here. Yeah. Okay, so what do we know? We already have a definition for n prime dot product with b. Here we ended up with b prime dot product with n, so we're kind of close. Yeah. But of course, applying that lemma one more time, we get that this is minus tau times the normal. Yeah? And what is b prime dot product with t? Well, that's the same as minus t prime dot product with b. Yeah? Remember, t prime is the normal. Normal dot product with the binormal is 0. Yeah. And that completes our three relationships up here. So this is our complete description of a curve in 3D. And really it's composed of these three directions, right? The normal, the tangent, and the binormal. And two numbers instead of one, right? Curvature, which is the same curvature we had before. It's just like the steering wheel direction, you know, the amount that the curve is spinning in the plane. And then torsion, the way to think about it is the amount that my curve is lifting out of the plane. Yeah? And there are many intuitions you can give for it. So one way to think about it is, like, notice that this is the change in the normal direction, dot product with the binormal, right? So if you kind of draw the right picture, this is kind of measuring everything that's happening orthogonally to the curve's tangent right here. And so that's why you can kind of think about that as lifting out of the plane. Right? So what do you think the fundamental theorem of the local theory of 3D space curves is? Anybody want to take a guess? Yeah, if you know the curvature and torsion function, you know the curve up to a rigid motion. Yeah. We're not going to prove that one here because like enough already. But essentially, the proof is quite similar. You just kind of reverse all the definitions we already had. I see some suspicion back here. We're good.
Just for so you use that b is orthogonal to the derivative of b. So are we sure that b has a constant norm?
That b has a constant. It does by definition, right? Because t and n have constant norm. You took their cross product and they're orthogonal to one another. Yeah, great question. Any others? Cool. Okay, yeah.
What is rigid motion here?
Translation and rotation.
Okay.
Yeah. Okay. Does reflection affect it? Yes, it does. There's a sign change that can happen depending on how you define this stuff. Okay. Right, and that happens because the cross product is right-handed. One question, which I know was on the forefront of everybody's minds, because I'm desperate for somebody to use this super cool formula in differential geometry, is does this story lift to higher dimensions? And the answer is yes. Essentially, just the way that we got the tangent, the normal, and the binormal, if you have a curve in like the 5th dimension, you can get 5 vectors. And the way that you do it is you just keep differentiating your curve with respect to arc length, and then kind of orthogonalizing everything that came before it. Right? That's roughly the process we use to get this thing. And one of the surprising things that happened that I wish I could explain, and I can't, is that the set of Frenet relationships is tridiagonal. If anybody has any great intuition for why that should happen, I would love to hear it. I really don't. In other words, like if I have the curvature, the normal, the binormal, the binormal, whatever, then somehow like this guy only has a component in the last 2 rather than like, 1 4 away. And I don't have a good geometry picture for why that should happen. I wish I did. Anyway, I love this formula, and I'm really hoping someday somebody in this class will have a good use for it in some kind of high dimensional curve, like time series or something. But I haven't found it yet. And actually, when we were preparing your reading, I spent more time than I'd like to admit trying to find at least one paper that uses this, and I couldn't. Okay, great. So you might have forgotten, but we are in a computer science class, and finally, we can ask the question that I know is on many of your minds, which is, what do these things actually look like in software? Like, what does it mean to write an algorithm that deals with a curve? Yeah, and that's really our point in this course. We're moving quite slowly through the kind of intro-level differential geometry just so you get some intuition for the kind of calculations that we do. As we move farther and farther in this course, the weight will go more and more on the discrete side. But of course, at the end of the day, as computer scientists, well, we've defined curvature and torsion, but I haven't really told you, like if I'm a computer graphics person and I have a camera curve in 3D and I want to analyze it or smooth it out or whatever, how could I use these things to help me do that, right? And that of course, at the end of the day is probably what we want. Or to compute this 4th dimensional Frenet frame. Right, so if you took my class in the fall, or if you've taken just about any computer graphics class, probably curves look something like this. Right? So this is a cubic Bezier curve, and essentially it's kind of like a curve that goes through 2 points, has 2 prescribed tangents, right? That's 4 constraints, so you need a cubic curve. This is a good exam question, right? There's a constant term there. But in any event, up until maybe 20, 30 years ago, really most of the people that thought about geometry were in this world, right? And if you take a class in computer-aided geometric design, CAGD, you'll spend a lot of time thinking about what does it mean to build curves and surfaces out of these sort of piecewise rational or polynomial objects. And indeed, it's an interesting and extremely non-trivial thing to do, right? And especially if you're in computer-aided design where you really want those nice smooth surfaces, this stuff is really critical. So here's my question for you guys. So let's say that I have a cubic curve, whether it's Bezier or another one. If you took my undergrad class, then you converted between all the different types of cubic curves more often than you like to admit. Here's my question, is what is the arc length of a cubic Bezier curve? So I give you the 4 control points here. I'm looking for a formula for the arc length of this thing. I mean, the formula for the curve itself is pretty nice. It's gross. Thank you, Leanne. In fact, it's not known. So this is like, this is one of these things from calculus that like, looks innocent enough. It's right, there's like a square root hiding in here and a cubic underneath it. Actually a 6th degree thing because you got a square to get distance, yeah? And this is not an integral we know how to do in closed form. You can approximate it reasonably well, right? I mean, you could sample a bunch of points on this curve and sum up a bunch of arc lengths. Do some kind of quadrature there, but there's no nice formula for it that I know of. Yes?
What do you mean by closed form? That there's no elementary...
Yeah. I mean, you could define there to be a function, which is the thing that goes from 4 points to the length of the Bezier curve, and that's a well-defined function. But sort of writing it in terms of the basic kind of elementary stuff, right? Cosine, sine, square root. As far as I know, there's no nice form. So we're in a little bit of trouble from the get-go if what we're trying to do is shape analysis. And in fact, really there's a sad fact, which is you take these nice differential geometry classes, you learn all these beautiful formulas and theorems and things, and very rarely can you actually compute them. And when you can, they're usually quite messy. And to make matters worse, like, okay, if you have a cubic Bezier curve, well, that's like a really nice arc, but like, let's say you want to make the letter S, what do? Well, you need 2 of them. Yeah? And so what do? You make another set of 4 control points that start here and maybe do like one of these. What's the curvature at this point? Well, often it's ill-defined, right? You might not even have a second derivative, even if your curve looks okay. Yeah, so somehow this is just like an ill-suited theory from the start if what you care about is the nice kind of differential structure on curves. Those of you who took my undergrad class are now like, why do we waste all this time on that? Okay. Of course, these are only approximations anyway. I think when you take graphics class, you learn a lot about Bezier curves and what are the other bases that are out there, logarithmic spirals and like all these different special cases of smooth things that, you know, obey different pairs of points and tangents and whatever. But the reality is that none of them captures the whole set of smooth curves in 3D anyway. So what do you think our solution in this class is going to be? Well, what we care about is the analytical side, and somehow like all is for naught anyway. We use a nice smooth curve and we still can't do computation on it. In some sense, we might as well just replace our curves with like the world's least interesting version of curves, which are also equally good approximation in the sense that if I take any smooth curve, I sample enough points on it, and I connect them by little line segments, it's actually a pretty reasonable approximation. Yeah? And since I can't do a lot of my computation on a Bezier object, well, I might as well not be able to do my computation on a much simpler object and work with that instead. Yeah? It sounds goofy when I put it this way, but it really is more or less the philosophy people have pursued in this particular world. Yeah? So in our chatting about discrete curves here, we'll mostly focus on this case of a polyline, which is a fancy term for just a bunch of line segments connected, you know, head to tail. Cool? Here's the thing. Let's say I wanted to do differential geometry on a polyline, right? I have all this beautiful theory. I talk about cars driving around in smoke and magnets doing, you know, donuts on the blackboard. And there's only one big problem, which is on this curve. If I really were driving a car along precisely this curve with unit speed, I would die very quickly. You guys see that? Because for a long time, it would be pretty boring. I'd be driving with straight, you know, constant speed on a straight line, and then suddenly there'd be this infinite amount of acceleration as my car jerks its steering wheel and moves on to the next direction. Yeah? So if I just verbatim take this differential structure that we've defined on the board and read it off on this curve, what do I get? I get flat, 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 infinity, flat, 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 and so on. Yeah? So something needs to give. Yeah? So far, all I've done is complain. I haven't told you, you know, how to fix anything. So there are a lot of different ways out, right? I mean, for one thing, you know, all of these formulas are in terms of derivatives, right? We have pretty reasonable ways of approximating derivatives, right? I mean, t, it kind of looks like f of t plus h minus f of t divided by h, right? So we could kind of say, well, maybe I think of these points as, you know, samples of a function gamma of t. So I kind of do a divided difference and obtain a reasonable notion of curvature. And indeed, plenty of people do that. What do you think happens when I do that and then I want to recover something like the turning number of my curve? Well, I'll get like an integer-ish when I integrate over the curve, right? But there's this pesky squiggly equal sign here, which is telling me that no longer will all of my nice topological properties hold. Yep. And so it used to be that the way that we would get around this problem is we prove a lot of theorems that look like this, right? As delta h goes to 0, something. And indeed, if you take a numerical analysis course here at MIT, you know, I'm just on autopilot. This will be more or less where you'll be spending your time writing proofs. But there's a big problem with this theory, which is, of course, in the shape analysis world, like, okay, maybe less so in curves, but eventually we'll talk about like point clouds and 3D surfaces and like the, you know, the Stanford bunny, which is legitimately from Stanford, and a bunch of triangles, yeah? Does it make sense to talk about limits as h goes to 0? Well, in some sense, no, right? Because the data I have in front of me is all the data I got, right? I can't, like, if I decide my measurement is accurate, like inaccurate, go back to the bunny and collect some more points. I can't do that. Right? And so the reality check here is that often h is positive, and that's just life in the city. And so it makes some sense to consider basically two different objects in parallel. One is the sort of classical one, which is this notion of convergence, right? As delta h goes to 0, my approximation of curvature, you know, converges to actual curvature. But there's a second one, which I would argue is, I don't know about equally important, but similarly important, which is the behavior in the regime where h is positive, because that's where our data is, right? And that's the one that we're going to think about today. Yeah? And in fact, our goal is going to be to think about discrete theories of differentiable curves. This is a totally contradictory phrase, right? We're talking about discrete things and differentiable in the same breath, or in two breaths, because I'm all excited. Okay, notice that I snuck one thing past you guys, which is theories. And one thing we're going to see is that what we'll outline today in class is incompatible with your homework, even though they both work on a smooth curve, which is, disappointing. But that's life. Oops. Okay, so let's do a little bit of recalling. Since our classes move so slowly, it's easy because it was the beginning of lecture today. Remember our picture here of curvature of plane curves. We have a tangent direction. The tangent is cosine and sine of theta. And we defined a thing called a winding number, right? And that was the change in angle. So one picture which is perfectly well defined is to take this object, right? This notion of a Gauss map where you're just computing the number of times you turn around and kind of lift this object to a discrete curve, right? And here's what the picture might look like. So this is a discrete Gauss map. Notice here I've used the normals to the curve instead of the tangent, or when I say what I really mean is Eton at Columbia. But the reality is that these are just 90 degrees off from one another, so that's sort of an okay thing to do. Yeah? And what does the Gauss map look like? Well, somehow on all of the line segments here, right, it's just a constant. And then rather than like getting all upset that suddenly there's a discontinuity here, there's actually a pretty reasonable thing you could do in between, which is to say your Gauss map at this vertex is kind of like a whole swing worth of normal directions changing at that point. Notice this is a little bit BS, right? Like for all I know, the normal looped over and then went there, right? There's nothing in this picture that precludes that. But taking the closest matching normal, I think, is a pretty reasonable picture that we'd all agree is an okay thing to do. Okay? So there's some nice structure that's worth noting because it's going to carry over when we talk about finite elements. For one thing, notice that there's this weird duality that happened, that what used to be an edge became a point in the Gauss map, right? Because this entire edge is one normal vector. And what used to be a vertex became an edge in the Gauss map. So it's just a thing to keep in the back of your head in case you like to be confused, is that somehow these two things swapped roles. This is a very typical thing to happen in geometry world. But actually, there's an even nicer observation than that, which we already alluded to in our first lecture in this class. But now let's get to it in a little more detail. So, anybody remember what these things are called for a polygon? This angle here that I've denoted. So I take an edge, I expand it a little bit, and then I measure the angle with the next edge. The exterior angles. And for any polygon, what's the sum of the exterior angles? This is 10th grade math. Maybe 9th, maybe 12th, 2 pi. Yeah? Of course, that's not 100% true. If the polygon loops around itself once, then what is the sum of the exterior angles? What was that? 2 pi k. You're jumping, that would be loops around itself k times. But you're absolutely right. Yeah, the sum of the exterior angles on your polygon, well, it's 2 pi, times an integer. And that integer is what? It's exactly the turning angle of your polygon if you're walking around it and you're making reasonable turn at each point. Does this sound familiar? Yeah, it's exactly the same as the turning number theorem, which I erased on the board. Okay, and so a typical kind of sleight of hand that happens in discrete geometry is to say, oh, wait a second, I have a classical theorem about polygons, and my input data is a polygon, and this theorem matches a theorem that I have in the smooth case, right, where I had some angle-based quantity, in that case, right, the curvature, I integrated it, which is kind of like summing, and I got 2 pi times the turning number. Okay, so maybe what I should do is define curvature in terms of this angle. Yeah? And indeed, that's a perfectly reasonable discrete notion of curvature. There's only one problem. Let's say I take this is obviously a very coarse approximation of a smooth object. Let's say that I start adding more and more and more points. Yeah? So it becomes slowly kind of a smooth, I don't know, Pac-Man kind of shape here. Yeah? What's going to happen to the thetas? They're going to get smaller. They're going to go to 0. Right? Because adjacent segments they're going to unfold. So is theta curvature? No, right? Because Pac-Man has curvature. Pac-Man's smooth. What's that about? So one way to think about it is that theta is a curvature. It's sort of the integral of curvature along this segment. Yeah? And this is a very typical thing to think about in discrete geometry, is that we talk a lot about integrated quantities instead of the quantity itself. I can't sense curvature at every point along the segment, right? It's 0, 0, 0, 0, 0, infinity, 0, 0, 0, 0, 0. but somehow that's like not a very interesting picture. And so we say, well, somewhere along this segment, theta happened. And so that's somehow the integral of curvature along this object, right? So if I wanted to approximate curvature, what would be kind of a reasonable way to do it? We'll just divide by the length of that segment, right? So roughly curvature, and this, notice there's the squiggly equal sign that we don't like. What can we say? We can say that, well, somewhere the change of angle was theta, so this is a reasonable definition of integrated curvature. Over here, we can say some approximation of curvature at this point might be theta divided by these lengths. And the nice thing is if you do your experiment, I encourage you to do this in MATLAB or Julia or whatever at home. If you refine your curve more and more and more, the thetas will go to 0, but this number will converge to a scalar, and that's exactly the curvature of your curve. So that's the way that this picture makes some sense. To add a little bit of detail here, let's say that I refined my curve and actually that 90-degree angle stayed there, right? So I added more points. What does that tell me about this curve? Well, in some sense, the theta remained the same. Yeah? What changed? The curvature. And that actually makes some sense, right? So the kind of picture that you might have in your head is something like this, that by refining my curve, I actually learned that, in fact, this segment was smaller, but encapsulated the same change in angle. Yeah? So it's kind of a nice self-consistent story. Okay. So that's the basic picture here is that we're somehow thinking about integrated quantities. These live at the center of an object that I'm going to call the dual cell corresponding to this vertex. This is a little bit pedantic for a curve. So the dual cell corresponding to a vertex is like the two half-line segments adjacent to it. The picture that you should keep in the back of your head, we're going to spend a lot of time talking about triangle meshes. Let's say this is a vertex on a triangle mesh. Then the dual cell is somehow this like pentagonal object that's sitting around a vertex, right? And what we're going to find is, for instance, it's quite easy to get the integral of Gaussian curvature in this cell, even if it's hard to approximate it at a point. Okay, so a similar thing's going to happen. And indeed, if you want to be really crazy, you can get a discrete turning angle theorem, right? Because the integral of curvature over your entire curve, well, it's certainly the sum of the integrals over all the segments. And then we kind of define that to be theta. And now, by a discrete theorem, like the sum of the turning numbers, what do? You get 2 pi k. Yeah? So there's order in the universe. There's a little bit of tautological reasoning going on here. Like I chose curvature to be the thing that preserves this, so it's not terribly surprising that when I sum it up, I get 2 pi k. So on your homework, you're going to prove a different property of curvature, right? You're going to show, like, let's say I have an arbitrary curve sitting in 3D, and I want to shorten that curve. Right, so I'm gonna, I draw a curve in 2D actually, right? And now what I can do is I can infinitesimally displace every point along my curve any direction I want, right? So let's say that I displace every point along a tangent to the curve. What happens to its length? Nothing, right? Because essentially I stretch the curve, but the length of it as it's traced in 2D is the same, right? Whereas like if I displace it this way, right, the curve shrinks, right? Eventually it converges to a straight line. Yeah? So just like we talk about gradient descent and optimization, which all of you guys know what it is now because we mentioned it in the last class, I could do gradient descent on arc length, right? And what do I get? I'll get a vector field along my curve, which is roughly telling me what direction I should flow the curve to increase or decrease the arc length the most, right? By the way, by the argument I just made, should that vector field have any component in the tangent direction? No, right? Because that won't change the length. It'll just kind of reshuffle points along the same curve. Yep. And what you'll show on your homework, spoiler alert, is that if you want to decrease arc length the most, you should flow every point locally along the curvature normal. As a sanity check, what's the curvature of a straight line? Come on. Really, guys? All right, 1, 2, 3. The curvature of a straight line. 0. Thank you. That's a sanity check here, because how could I flow a straight line and make it shorter? Like, I can't, right? Yeah, so the basic picture here is that the curvature normal is telling you how to shrink a curve. In fact, you'll code that up. So you'll code up a discrete curvature normal, and then you'll step the curve along it, and you'll see it shrinks. Not terribly surprising. Here's the thing. I could just as well have defined a discrete curvature using this relationship, right? So in particular, I could think of arc length. Let's say that I have a curve, and here's a sequence of points. So like x1, x2, x3, right? and so on, right? I could think of arc length as a function, I forget what I call it in homework, probably S, of, right? This is just an honest to goodness function now of these points, right? And it's just the sum of the lengths of the line segments. Yeah? And I could take the gradient of arc length with respect to the positions of these points, and indeed, what will I get? Well, I'll get that this point wants to move up, that guy wants to move down, nothing too surprising there. What is the norm of that vector? Well, one thing you'll show in your homework, if you're wondering, like your homework tells you to solve this, I'm not giving it away. You'll show that the norm of that vector is 2 sine of the turning angle over 2. You should get depressed and sad and disappointed right now. Do you see what just happened? We went to all this work to come up with a notion of curvature that preserved the winding number theorem, right? And we said, like, well, if we come up with this nice notion of curvature, then we can compute winding numbers and like get it with an exact equal sign, and life is good. If I choose that notion of curvature, can I also get that curvature is the gradient of arc length? No, these are incompatible. They're just different formulas. Do you see why this is a downer? There's no free lunch here. I have 2 different choices of curvature. They both capture what I believe to be the same thing about a discrete curve, but unfortunately, the formulas for these 2 things are not the same, right? And what that means is, as engineers, we actually have some work to do, right? Because when you come up with a piece of software and you're measuring curvature, that's not enough. In fact, if you guys want to feel very fancy and you're like consulting for a CAD company and they say, I'm computing the I don't know, mean curvature of the side of the car or whatever, you can say, well, which curvature? And that's a totally reasonable question to ask, because basically different ones have different properties, right? So this guy will hold the turning number theorem approximately, and this arc length gradient exactly, whereas the turning number one will approximate this arc length gradient, but hold the turning number theorem exactly. Yeah? Even though both of those are true simultaneously in the smooth case. It's a total downer. Yeah? Exactly. So, right, is all for naught? Like, is like one of these somehow more reasonable approximation than another? I mean, one thing I haven't done is talk about either of these things in the limit of refinement. What happens in the limit of refinement? Well, theta gets really small. Yeah? What does sine of theta look like when theta is really small? Looks like theta, right? Physicists are really sloppy about that, like when you do pendulum stuff. Yeah? I'm going to give them a very hard time in this class. So what's 2 sine of theta over 2 when theta is small? It's just theta, right? So in fact, even though these functions are different in the discrete regime, they all agree as you refine your curve, right? So there's still order in the universe. Okay. So in other words, this is our first example of a no free lunch theorem, right? You can choose one. You can either have a discrete turning angle theorem, or you can have a gradient of arc length, but you can't have both. Yeah? And that's just life in discrete math. And it's not like we haven't discovered a notion of curvature yet that has this property. It's that these 2 things are mutually exclusive. I have a friend who's an algebra professor at Stanford, and he was talking about, apparently he gets some mail that are like, well, I know you haven't figured out how to trisect an angle yet, but like here's how you do it. And typically the instructions involve like getting out a ruler at some point. This is an example of a negative result. Okay. Right, so the remaining question that we're not going to cover because it's boring old school numerical analysis is do these things converge in the limit? And the answer is yes. You can essentially obtain that pretty simply by just taking the Taylor series of theta here. Yeah? Okay. Of course, it's easy for me to throw up my hands and sort of say, yeah, these converge, this is boring, whatever, this is just college calculus. There's actually a lot hiding here too. I mean, you could ask about the rate of convergence, how many sampling you need, does it work for smooth curves or a C1 curve or whatever. And again, if you take a CAGD course, I believe we have some in mechanical engineering, you'll spend most of your time thinking about that kind of stuff. Okay, and this is the high-level story of the world of discrete differential geometry, right? That you have different discrete behavior, but similar convergence behavior. And that choosing one of these is going to matter a lot. We're going to see a few more examples of that in the next 10-15 minutes we have in class here. So any questions so far about our story? And to think, this is the simplest example, right? These are just 2D curves. Things are going to get complicated soon, as soon as I put together my slides. Okay, so now let's talk about 3D curves. I don't know what these 3D curves are, but I thought they looked cool, so I put them on a slide. I don't know. There's this guy who has this web page, and apparently he's an artist that just likes strange attractors, which is cool. Right, so as a reminder, the basic object that we talked about in the differential geometry of 3D curves was this object called the Fernet frame. One interesting thing that you'll find, in fact, you'll find this in the reading for this course, if you look at a lot of the papers that we linked, there are actually relatively few discrete applications of the Fernet frame. Can anybody think of some reasons why? Like, this isn't terribly practical for a lot of, like, I don't know, typically curves show up in physically based simulation or architecture, that kind of stuff. I promise we'll hit machine learning when we talk about, like, machine learning needs dimensions bigger than 1, so that's life. Yeah. The Fernet frame is a perfectly elegant, beautiful way to understand a curve, except for one very important curve, which is a straight line, right? The Fernet frame is ill-defined for a straight line. You should like let that sink in for a second, right? I mean, so the Fernet frame in 2D makes perfect sense for a straight line, right? Because we got the normal by just rotating 90 degrees. But in 3D, rotating 90 degrees is ambiguous, right? There are many different ways you could do that. And if you take a look at our derivation, what did we rely on? Well, we relied on these kinds of statements which break down when things just vanish, right? I can't divide them by their length at that point. Yeah? And so this is actually quite problematic. So if you have applications that need the Fernet frame, oftentimes what will happen, like maybe I'm driving a car and I'm computing its Fernet frame, and then it goes into a straightaway for a little while, and then it keeps driving. Computationally, there's often like a discontinuity that happens because, you know, along that straight line, it's completely ambiguous what that Fernet frame should be. Fernet shame. Right, but there are a few. I did manage to dig up a few discrete Fernet frames. We won't talk about them a whole lot. Some of them appear in protein structure analysis. I would love, if there are people in this class that know stuff about this application area, I would love you to tell me whether these are interesting or not. These are well cited in geometry literature, but I think only because we couldn't find anybody that uses Fernet frame discretely. So what these folks do is they have a discrete curve. The tangent is sort of well defined, right? That's just like take adjacent points, divide by their norm. What these folks do is kind of an interesting circular trick here. They say, okay, I'm going to define the binormal before the normal vector, because I know that tangents are somehow well defined, right? We know that the change in tangent is the normal vector, but that's kind of hard to capture. But if I think of two adjacent line segments as forming a plane, then the normal to that plane is kind of binormal to those two segments. Yeah? So what they do is they say, okay, the binormal is the cross product between two adjacent tangents, and then the normal is whatever's left. Yeah? It's kind of a sneaky trick. And it actually is kind of a reasonable thing to do. And these papers define these two objects called bond and torsion angles, which are roughly curvature and, well, I guess torsion. Yeah? Yes? Oh, we were just working out curves in 3D. That's my colleague Amir gives me a hard time for making apparently what are rude gestures in Israel while trying to explain differential geometry. Okay, and so you can look at some interesting discrete structures because essentially there's some rotation matrix that's taking you from one normal, tangent normal, binormal to the next, and there's some interesting things that happen there. One of the really bizarre things that these guys prove is that this is actually well defined for a fractal curve. I don't know why you want that, but it's kind of fun. I don't think we're going to spend much time on that. Because essentially, the reason why all of this stuff doesn't pop up that much is the second that curvature is 0, well, remember that I defined n to be t prime divided by its norm. Right? So curvature is 0, then t prime is 0, and I can't divide it by its norm anymore. Right? So in some sense, curvatures with well-defined, or curves with well-defined curvature are in a very frustrating state, right? They can never stop moving. And to put them out of their misery, we're going to talk about a different frame on a curve, which does make a lot of sense. And this is the last missing piece you need on your homework. So we'll start today, probably wrap it up next time, and then finally move on to surfaces, which I think is what everybody thinks of when they think of differential geometry class. Okay? All right. And in case you were wondering, like, okay, Justin, you spent 3 lectures talking about curves. Why do they matter? I present to you the most practical application of all, which is in simulating shoelaces. Yep. And this is a great example where initially it might seem like shoelaces are one-dimensional objects that you want to simulate on your computer, so you should use all this machinery we developed. That turns out not to be the case for some subtle reasons. You can just barely see it in the rendering here. What do you see about this rendering? Is it just a tube? There's also some color there, right? And notice the color's kind of twisting around. Yeah? And in particular, if I take a piece of string, here's one, this is dangerous. Yeah? Now, does the theory that we've laid out on the board account for the fact that if I twist this object enough, let's see if I can simulate this. I always wanted to be one of these professors that got to do this kind of stuff. And I take the ends in, aha! What did I get? I got this buckling phenomenon. Yeah? Whereas if I just let it relax and I bring them in, that doesn't happen. Yeah? Well, doesn't happen. Yeah. Okay? Is that captured by this theory here? No. Right? Because what do I need? In addition to having the shape of the curve, I need to account for the fact that I made a twist, and that hasn't been accounted for in talking about just curvature. Yeah? And that motivated a different discrete model for curves that turns out to be kind of a nice model for curvature too. Yeah? And it makes really cool stuff. So like here's a video that I stole from their research here. So they're torturing a piece of string. I think it's a frictionless piece of string, which is why it's somehow sliding around a lot. And indeed, it forms this object. Anybody remember from lecture 1 what this thing is called? You're killing me. It was the same thing that used to show up like, you guys probably don't even remember phone cords. Right, this would always happen. This is called a plectoneme. It's a very specific physical phenomenon where you take an elastic rod, you twist the end, and eventually it buckles in on itself. Right? There's some interaction between elasticity and geometry happening here. Okay. So if you want to formalize how to think about phenomena like this, what you need is not just a curve, but actually a framed curve where the frame is giving you the twist of the material frame as you move along the object. That's kind of like the color here, right? So the idea is that not only will I have a function gamma of s, okay, the tangent is well defined, there's not much I can do about that, but there's two orthogonal directions to the tangent which are going to describe the twist, and rather than just making them the normal and the binormal, I'm going to add them as parameters to my physical system which are capturing how this thing is bending around. Yeah? So it's kind of like the position of the red and the blue stripes. Okay. And there are a lot of different things that I can measure about a curve. When I do simulation, right, if you take the kind of Hamiltonian view of the world, then physics is trying to mess with energy. So a reasonable thing to do is to measure like how bendy my curve is, how twisted it is, and so on. And those are all expressible in a very nice way in language of differential geometry. So here, one reasonable definition of a bending energy, right? So this is a number that is big when my curve is bent up. What do I know? I know when my curve is flat, the curvature is 0. When it's bent up, curvature is pretty big. Yeah? So a reasonable bending energy is to take the curvature squared, just integrate it over the curve. Yeah? And there's a nice expression for that. So remember that your curvature normal is nothing more than t prime. Yeah? I'm going to just like, we only have 2 hammers. We're going to hit like a bunch of nails today. Yeah? What do we know about t prime relative to t? Huh? Somebody speak up. Orthogonal, yeah? They're perpendicular to each other, yeah? So in particular, if I write it in the t, now m1, m2 basis, where I'm just going to say these are generic directions that capture the twistiness, then this term is 0. Thank you. Whew. Okay, and what I'm left with are these two things, and we're going to just define 2 numbers here, omega 1 and omega 2, which are the curvature, give the curvature vector in this funny material basis. Okay, and similarly, right, so I can basically take curvature and just replace it with this squared sum here, and nothing has changed, yeah? Similarly, if I want to measure the twist of my frame, how can I do that? Well, one thing I could do would be to look at the material frame and take its derivative along the curve, right? So this is like the twistiness of that orthogonal thing. First of all, what is the component of m1 in the m1 direction? 0. Get the trick? So I want to know the change in m1. All I have to do is take its dot product with m2, because it's also not changing tangentially, right? It stays orthogonal. Yeah? One fun fact about this thing is that m1 prime dot m2 is the same as minus m1 dot m2 prime, and that's just a corollary of the lemma that we already wrote down. Yeah? So I can write something that looks a little asymmetric, which is to take this number and square it and integrate it over the curve, and then you can double check that if I'd like swapped the role of these two guys, and nothing would have changed. Cool? So this is some number that's measuring the twistiness of my frame, right? The more convoluted this M1 frame is, the more times it turns around, the more rapidly M1 is changing, and that's what's captured here. Cool? So there's one more question, which is if I really want to take a differential geometry perspective here, I need to figure out the basis where I write all of the quantities in my curve, right? And notice I've made some effort here to write everything in terms of like tangents and normals and binormals rather than just x, y, and z. But there's a question, which is if I want to describe this material frame, M1, M2, right? These are two directions that are orthogonal to the tangent. So there's like a little plane. What basis should I use for that plane to do that? Right? So one basis would be the normal and the binormal, and that's perfectly reasonable, but it's not well defined, right? So in this particular piece of research, they have like a more hipster basis. I really love the title of this paper, and I like couldn't choose which meme was more appropriate. But essentially, what Bishop proposed relatively late in the game in differential geometry is that there's actually more than one way to frame a curve. I think this is like, you know, Who Framed Roger Rabbit kind of thing. That the Frenet frame isn't the end of the story, and in fact, there are a lot of other ways to put a basis on a curve, mostly for those two normal directions, like the normal and the binormal, that make perfect sense, even though they didn't come from this procedure here. Okay? And so we'll talk about the Bishop frame, which has a really interesting trick. So the idea here is that, okay, the tangent is like the one well-defined direction we can all agree on a curve. Yeah? But then that gives us these other two directions, u and v, that we can work with. And essentially what Bishop proposed is to do the following. He defines this really bizarre object called the curvature binormal of my curve. This is essentially exactly what it sounds like. So rather than take the normal to my curve, take the binormal and just weight it by curvature. Notice that doesn't show up in the Frenet frame. This is just like a weird thing that he defined. And he wrote down an ordinary differential equation to define T, U, and V here, right? So one thing that you can double check is that T prime equals the curvature binormal cross product with T. Do you see why that would be the case? So first of all, what is the norm of T prime? Well, it's curvature, so we got the scalar part right. And why is there a cross product? Well, we know it's parallel to the normal, but we chose the binormal, so there's a 90-degree rotation that has to happen, right? So remember that if this thing is parallel to the binormal, T is the tangent. If I take the cross product of those two guys, I'll get the normal direction, right? Weighted by curvature. Yeah, sneaky, huh? So this is secretly just a complicated way to define the tangent direction. And then in addition to that, Bishop sort of said, okay, great, I have one direction defined with that ODE. Let's define the other two the same way. So in other words, I just place a frame at some point on the curve arbitrarily. I do that while my feet are pointing the tangent direction. And now I'm going to solve this equation to take that frame and propagate it forward. Let's check some boundary cases. When the curvature is 0, what are u prime and v prime? 0. Do you see that? So what does this ODE do? It says, if my curve is flat, leave the frame alone. Yeah? And similarly, as the curve is bending, one thing that you can check is that this is sort of the most relaxed frame. If you go back to that twisting energy, and you do a gradient descent on that thing, where you fix the frame at one point, and then you have the twist everywhere else, that process will converge to exactly this Bishop frame here. Yeah? This is not something we're going to derive because we've done enough calculations in this class. Okay? But the nice thing to know is that it satisfies a very simple set of relationships. Yeah, Leon. Ah, that's a great question. Even if I don't have a normal, is curvature well defined? Yeah, it's just the norm of the derivative of the tangent. Right? So long as you have a tangent, you have curvature. It just might be 0. Yeah, but you don't have a normal. Yeah, that's where it's a little bit weird, right? Okay, right. And so one way to kind of see that this is the most relaxed frame is just as a corollary of these relationships here. You can check that u prime dot product with v is equal to 0. And so in other words, think about what that's telling you intuitively, right? So u and v are these two normal directions. What it's saying is that the change in one of the two normal directions, the component of that in the other normal direction is 0. Right? So in other words, there's no unnecessary twist happening. Cool? All right. Yeah, and this was the Bishop frame. It came relatively late in the history of differential geometry. Yeah?
If I'm navigating on a plane and my curvature is non-zero, but my binormal is 0,
yeah.
then even as the curve bends around,
This thing will twist.
u and v won't do anything because omega is zero.
Nope, that's not quite right. So if I have a circle on the plane, curvature is non-zero. And in this case, I think they define the binormal. Oh, I see what you're worried about.
Oh, the binormal is just the unit vector sticking out of the plane.
Yeah, but you are right that I don't know why that's defined. Oh, it actually doesn't matter, because, well...
You need 3D for a cross product.
Yeah, exactly. I think that's the main point here is this doesn't work in 2D. Yeah. And that makes sense. If you compute the Bishop frame of a 2D curve, you'll see that it comes out of the plane. I encourage you to do that on your homework. Okay. Right, so once you do that, then when you have this material frame, M1 and M2, which are expressing the twist of my physical object, well, I can just get that as an angle theta away from the kind of most relaxed frame. And somehow physically this makes sense, right? What it's saying is that I'm expressing the twist of my knotted up piece of string as deviation from the most relaxed piece of string. Yeah? And indeed, if I do that, then the twisting energy is nothing more than the total theta prime, which makes a lot of sense. Right? So everything kind of fits together. So the really nice thing in 2 minutes or less, and then I'll shut up here, but I want you to be able to do your homework, is if you want to discretize this thing, it's actually pretty straightforward to do that. Right? So here I have a discrete curve. I'm putting all the vertices at the xi's, all the edges are e's, so these are just differences in adjacent x's. Okay? There's another very typical piece of notation here which clashes with the Einstein notation we talked about before. Here they're using upper indices to be dual objects and lower indices to be primal ones. I'm going to stick with that notation because that's what's in this research paper, and I've asked you guys to read it, although it does contradict a little bit what we talked about a few lectures ago. Sorry. Then, okay, again, we can all agree that the only well-defined tangent on a discrete curve is just the unit vector parallel to each edge. So we're going to keep that. Okay, one of the interesting things here is that there's a very unique choice of integrated curvature, which is 2 tangent of phi over 2. And this is, in this case, to preserve structure from the physical system. And I'll let you guys read this paper to justify it, since I'm a little out of time. What do you think the first term in the Taylor series for tangent is? Just linear again, right? So this is yet another formula for curvature that agrees with the discrete one. And then kind of similar to the paper we talked about before, they'll derive a binormal vector, in this case the curvature binormal vector, by taking cross products of adjacent edges, the intuition being that there's some shared plane between these two guys, and that's what's giving you the binormal. The convenient thing, and the really nice observation here, what if 2 edges are parallel? What's this cross product? 0. So in some sense, exactly the place where that shared plane is ill-defined, the curvature binormal still makes sense, right? So it's kind of a sneaky trick that happens here. Okay, so maybe we'll stop here because everybody's zipping up their bags and it's making me nervous. So we'll finish talking about this paper next time. You have enough to read the notation and essentially type in the formulas into your homework. And next time we'll talk about what it means, and then we'll talk about surfaces. Does that sound good? Fabulous. So we'll see you guys next week, rather than rushing through.